Redis and feature store, two terms that you won't have heard together before. But here we are giving a data point for a large scale feature store in Redis. Talk QPS in tens of millions and storage of over billions of features. Here's the agenda. We're going to first start with introductions. Then we're going to give a background around what do we mean by feature stores. We'll follow it up with why did we choose Redis as a feature store, and then jump right into the optimizations we did. The approaches that we used are based around compression, serialization, and Redis hashes. Then we're going to talk about what if we want to scale even further beyond the current scale, and then end with some key learnings and takeaways. So who are we? Where do we work? I'm Arbaz Khan. I work as a machine learning platform engineer at DoorDash. I have spent past few years building machine learning systems from ground up. Love the scaling and optimization challenges that come my way there. In my off hours, I am an avid cricket watcher, and I play often as well. I've also been posing as a traveler during COVID times, just to entice my friends to accompany me and to push me even further to exploit remote work benefits.
Hi everyone, my name is Zohaib Sibte Hassan and I'm a tech lead manager at DoorDash. I'm a father of four and I love open source software, hence why I am here. I also love solving these high performance problems. I would say building this feature store was one of the interesting problems that we solve at DoorDash. And what we hope for is that by the end of this session, you would have something to inspire on or look at as a reference when you are solving a similar problem. Arbaz is going to give you an overview and the solution, and I'm going to join you towards the end, setting out a future roadmap or further enhancements that can be done. So sit back, watch and enjoy.
Thanks, Zoe. A little bit introduction about DoorDash before we move forward. Our mission is to grow and empower local economies, and that's not just the current food business, but all kinds of small businesses. Our execution path is a logistics platform for on-demand delivery and a merchant portal for data-driven insights. Our long-term vision is to be the best logistics network for last mile services. Second, to be the go-to choice for merchants in mission critical challenges such as acquisition, branding, or delivery. And third is to grow our membership program to be the largest of its kind for connecting consumers to merchants. In terms of our current numbers, we are at 1.2 billion orders across 4,000 cities, and this produces tons of data which is sourced by our machine learning models. 40 of them are live in production today. They get hit at a rate of about a couple million predictions per second at peak, which costs us 7 cents per million predictions. It's all made possible by our machine learning platform. Multiple components in action here. The one component that we are going to talk about today is the machine learning feature store. So for folks who are unfamiliar what a feature is and what a feature store is, if models can be treated as functions, features are arguments applied to those functions. They are the direct input variables fed to a machine learning model. And as you can imagine, these variables or features need to be stored somewhere for fast and easy retrieval. That's where feature store comes in. It's a single source of truth for keeping the feature values consistent across production. And there are multiple purposes that a feature store can serve. The main purpose that we're going to discuss today is online serving, which is serving features for an online application where latency is the prime consideration. And there can be multiple scalability concerns that will be posed to an online feature store like what we had at DoorDash, two major constraints, QPS and storage. So if we take 2 million predictions per second and assume each prediction needs about 10 features, we're talking about a QPS of 20 million. For storage, 100 million entities featureized by 40 plus models in multiple different ways produces about 5 billion or more features for us. Apart from scalability, there are some peculiar challenges that a feature store poses. Features are read in what we call a batch random order. So as you know, there are multiple features that you would need for a prediction, and pulling these features, if you were in a SQL world, would have to be an in clause over multiple rows and not a between clause exploiting a sorted column, because there is no sorting criteria or a particular order in which features get pulled for a given prediction. The latency requirements are aggressive, single digit milliseconds per read, and the one benefit that you can exploit here is that the number of reads are much larger than the number of writes, which reflects read heavy request pattern. In terms of storage, features come in all different shapes and forms. You need to be able to support all these different feature types. Some can be simple, such as float values, or they can be complex, such as vector embeddings or integer lists, float based lists, and so on. Now, why did we choose Redis as DoorDash's feature store? Our consideration was to either pick an in-memory store or a disk-based store. As you would agree that in-memory stores are faster in performance to disk-based stores, and in case of Redis, they're also simpler in API design. One thing that puts people off is the costs of operation. Now, if you assume a high throughput scenario, the CPU utilization is the major bottleneck in costs, and in-memory stores consume fewer CPU instructions for the same operation as compared to their disk-based counterparts. This leads to a better CPU utilization. You can validate this by doing your own benchmarks. We did few, posting one where we compared Redis with CockroachDB for a set of operations for interest at a given rate. Found that Redis was 2 to 3 times more efficient than CockroachDB. And this is all assuming that Redis was used as is with its out-of-the-box offering, no optimizations. Once you start engineering towards optimizations, there's more capacity that you can extract out of it. And these are the kind of optimizations that I will cover next. These in turn combinedly, as I mentioned before, gave us 3x cost reduction. So let's jump right into it. First and foremost are Redis hashes. So typically the intuitive method to store feature values would be that you store feature names for an entity ID as a top level key and feature value as the value. But if you were to reorient a bit and anchor these feature value pairs by entity ID, then you can achieve better data locality per request. So typically features get all pulled for given entity ID, such as a consumer or a store in a store recommendation model. And in this request pattern, you are pulling features all from within the hash of an entity ID. This means that you would need a single HM get command instead of multiple get commands to Redis. In turn, this all improves your lookup performance, but also it improves your storage efficiency. I'll tell you why. Because keys at the top level at Redis get stored with additional metadata such as time to live, and when you consider hash keys, they don't store time to live or such metadata, which improves upon the storage overheads. But more than that, there's more memory optimization that you can do at the hash table level, which requires you to tinker with your Redis cluster config. There's a comprehensive article posted by redis.io under memory optimizations. I do recommend it to check it out. We did employ it and observed impressive gains with memory usage. Here's a sample of what results look like for just when studying incremental gains. We took a sample of 1 million features, posed them to Redis. The in-cluster memory was 30% better if these were reorganized as key hash pairs. We later combined this approach and put this in production, but for incremental gains, it was a good exercise. The other optimization that we did was to treat each feature based on its type. For example, vector embeddings, they are best encoded in binary format rather than JSONs or strings. But reverse is true for sparse features. Sparse features are those, again, which store more zeros than actual float values. This can harm your binary encodings. For illustration, if message pack was packing 0.0 float into binary format, it consumes 9 bytes. But if you were to encode it in a string, you will just need 3 characters, one each for 0.0. This just gave us freedom in how we treat each different feature type, and exploit that freedom to achieve greater memory utilization. One other clever serialization technique is that you do not use feature names as is, because feature names tend to be verbose, more meant for synchronization between data scientists and application engineers, not meant for storage. So for example, here a feature name for us looked as long as 46 bytes. This can well be string hashed into integer, and 46 bytes then can be converted into a 32-bit integer. This was one of the key approach in reducing our memory utilization. This is how the corresponding set operation will change. Just for again elaboration or illustration, that the feature name will be hashed right before it's put into Redis. The third avenue that we undertook was compression. Now, not all values can benefit from compression, but the low entropy ones, such as integer lists, which have a lot of redundant values, can greatly benefit from compression. We experimented with multiple compression algorithms. Snappy and LZ4 were the two ones that we took all the way. What you're seeing here in the graph is a cumulative outcome of all the optimizations that we have seen till now, but with Snappy as a compression algorithm and LZ4 as a compression algorithm. We found that Snappy was marginally better. Again, like any compression problem, this is all dependent on your data, and it's best if you benchmark these different compression algorithms according to your own data and get the right one. So all in all, Redis hashes with the configured hash sizes yielded the most gains for us, about 40% reduction there. The next best was string hashing in terms of incremental gains. As I said before, compression does not work on all feature values. So vector embeddings were one such which were left out in our compression approach, because vector embeddings are dense float values with high entropy, not really benefiting from compression. But all in all, we were able to achieve a 3x reduction in memory footprint and CPU utilization. We prorated these numbers based on 1 billion features for memory and 10 million reads per second for CPU. But they do indicate the 3x reduction here. So what are the next steps? We are focusing on sparse features. We, upon investigation, observed that our sparse features have about 90% zeros, and there's a lot of redundancy that can be exploited here with more specialized data structures or more specialized storage format. And that's one of our investigation path. The other is, till now, CPU utilization is the bottleneck, but as more and more features get pumped in, what happens when storage becomes a bottleneck? That's when a multi-level cache design is what is typically employed, but it comes with its own cons. And Zohaib here has quite a bit of insight into how these can be alleviated. What are the scenarios? On to you, Zohaib.
Thanks, Arvaz, for such a nice overview and deep dive into the problem. Um, let's quickly look at what happens if you cannot hold everything in Redis memory and you're using some database as a backup. In that typical case, you're going to use Redis as an intermediate cache layer where you read the value from the Redis. If it's a miss, then you go to the database and read the value from there and then write it to the Redis so that further reads can be served from Redis and then return the response back. One of the typical values, one of the typical problems there is cache stampede. And cache stampede is pretty well explained just by this one image. Imagine you have like two servers who are receiving a request. Imagine they receive a request at the same time. So they both hit Redis, they get the cache hit, perfectly fine. But now say the cache key expires and they receive a request. So the server again originates a request, gets a cache miss, and issues a read to the database. In the meantime, the other server also receives a request, also gets a cache hit, and issues an other read request. So now this is a duplicate read that you're doing right here. And imagine this being on hundreds and thousands of servers, and you have a thundering herd problem that's going to totally take down your database if it's not configured correctly, or if there's too much read like this going on over different values. And also, if you note towards the end, they're also doing duplicate writes because each one of them is just overwriting the value that the previous one wrote. So we're paying the double cost here. How can we avoid this? So one of the well-known or typically known techniques is people assume a random gap, and gap is a time window that where you feel like, hey, within this gap, I'll just do a random toss, and I would say, hey, if I'm above a certain value, I'll consider it as a cache miss. If not, then I'll consider it as a cache hit. And one of the simplest way to do that is imagine whatever the timestamp of your key is when it was written to the database, plus the TTL, whatever the timestamp on that key, plus TTL. TTL say it's 10 seconds, so you add 10 to it. Plus, you do a random into gap, and you take that gap, say 5 seconds is the gap, and I apply a random. So you multiply 5 with a random, and then you add it to the TTL. So it's kind of randomly forcing push over or the trip over from the now timestamp to kind of cause a cache miss, so that it's a simulated cache miss, so that the node can go read from the database and write it back to the Redis database, and the further reads have an extended time to live. Putting it in Python is pretty simple. Here's a fetch AOT key and expiry gap in milliseconds. So I read the keys TTL in milliseconds. So say if it's 10 seconds, it would be 10,000. And then I say random into 5,000, say this is 5 seconds. I'm just taking 5,000 as an example, 5 seconds as an example here. And I subtract it from the time remaining. And if it's greater than 0, means we still have not tripped over, then we say read it. Otherwise, we say none. And now you can use this function to kind of write that wrapper function around your database where you say, go read it from here first. If it's a miss, i.e. it's none, then you go back and read it from database. Otherwise, you just return the value back. So it should take care of your problem, right? Turns out, well, we asked this question saying, hey, can we do better than this? It does improve the situation, but can we do better? And answer is obviously yes. There is a paper called Optimistic Probability Cache Stampede Prevention, and I would recommend go read this paper. I won't go into the details on the lemmas and why a particular function is making it so efficient. So for all of that, please go read that paper. I'll just breeze over it just to give you an idea on how you can use this in this particular scenario. And paper actually kind of shows you the early gap expiration. In this case, it's showing the random with 20 seconds, 10 seconds, and the the proposed solution on how early expiry gap happens. And if you look at these dots on the stampede size, so on x-axis you have the early expiration gap, and on y-axis you have the stampede size. So you can see with the classic random thing, yeah, it is kind of spread out, but it's still a tower, and this is still a tower. But this particular technique would kind of push this down in both in terms of the cache stampede size and the gap itself. Here's the function, and again, I won't go into the detail, but the important part to note here is this one piece, if I can highlight it somehow. This one piece where you see delta, beta, and log of rand. And what I'm going to do is I'm going to make it easy for you to kind of put it in terms of the same function that we saw before in Python. And here it is, the xfetch proposed by this paper. Here you take a key, same, you get the TTL, but then you multiply a beta, which is by default 1, and this is changeable, and the effect of changing this is also documented in the paper. And then take the expiry gap, multiply beta with expiry gap, and do a log of random. And turns out just by doing this, everything else is exactly the same. Just by doing this, you're going to see an improvement. You're going to see an improvement in terms of the stampede size that it's going to cause. So the orange line shows you the uniform random, expiration, and the log random is right here. You can see the early expiration gap versus the stampede size. You're going to get a much more cleaner, steeper slope here. And again, I'll leave this for your reading on how this is more efficient. And you can rinse and repeat the same technique for L1, by the way, because yeah, wherever you can avoid network, and if you have an in-process cache, if you can use that, why not use that? Avoid network. Network is always expensive than CPU. So just by doing that, what I can show you is how this TD pattern or the spiky pattern is converted into something that's way less. You can already see the stampede sizes here, 2K expiry, and then it's continuously jumping between these highs and lows. But ignore the values on the side, they might be different, but what I can tell you is that the spike sizes won't be these uniform spikes and causing CPU spikes or network spikes or memory spikes, but all you would see is a random, more even out distribution. This is very much zoomed in. If you kind of zoom out of this picture, it almost looks like almost going into a straight line. So what did we learn? Well, first and most important thing, understand your cache payloads. Network is expensive when compared to CPU. So you might be thinking, hey, by compressing the payload, I'm putting more load on CPU. Might not be true. You might be saving more or shaving more time when you are doing compression versus just going over plain network over large payload size. Also, these minor things like log, randoms, all these CPU expensive functions that sound expensive might not be as expensive as doing it from network. So try to measure and benchmark, understand your payloads, understand your conditions, understand your system load. At large scale, these small percentages are the ones that have an accumulative effect. And you might feel like, oh, I'm just shaving off like 20, a stampede of 20, but when the request goes into thousands and millions, that's where all of this is going to multiply and give you an accumulative effect. And one thing that it's usually not well debated, but persistent storage is always expensive. Disk is always expensive than memory. It's a no-brainer. So putting something in your local memory and then something, or probably something, say in Redis, which is not writing to the disk all the time, is way more cheaper than any persistent store. yeah, the persistent store itself might do cache, which is perfectly fine, but it's building on the same principles. So you have to be the guardian of your own destiny. You have to know what kind of load or how sporadic or uniform load I'm going to put onto database. Can it have that much memory? And if it does, great, fine. But if it doesn't, then you put all of that in Redis. And there's a reason these caches have been around for so long time and people use them. Um, Same is true for keeping an in-memory cache. People use them. There's a reason why it's effective. So key takeaways are you have to experiment at your own under your conditions. You have to look at all these variables, and you might take a lot of pages from these solutions, our solution. More folks have done similar solutions, but your end result would totally depend upon the type of problem that you're facing. So don't underestimate the power of compression, ahead of time eviction in memory stores, and always pay attention uh, to what's your cache payload. Market shenanigan words are not going to get you anywhere. And we've gotten done a lot of detail in our blogs. We publish our blogs pretty often, and we have a complete 3-part series. If you look at, well, they're not 3 parts, they're like kind of individual pieces, but then they come together to solve this one whole problem. And that's the beauty of it. You engineer these problems and then you put them together to solve a bigger problem. And I would recommend reading these blogs. You can go check them out at DoorDash.engineering, and the URLs on your screen. And thank you all for your time. And I hope this has inspired and tinkered your thoughts around how you can build your own efficient feature store using Redis. Thank you.